Okay, so we are gonna talk a little bit about Scheil solidification, and basically those are kind of the equations that are solved in the Scheil calculation. There is a lot of theory about this. I don't want to cover too much about this topic, because basically what I want to show is more like the application in ThermoCalc. However, I want to open here just ThermoCalc and just talk a little bit about, what Scheil is, and basically, as the description of the package is saying, as ThermoCalc is calculating the Scheil for solidification purposes, and basically is really useful for slow solidification, especially for casting products. So basically, what Scheil solidification is going to tell us is the solidification range of the alloy, depression of the solidus temperature, and we're going to see that in the example, composition of the last liquid or any particular liquid to solidify, especially in the interdendritic region, and the phases formed during those segregation pattern. So we also can calculate some gradients, but those are the main topics that we can, main information that we can obtain from the Scheil. And that's going to be really important for segregation and obviously in heat treatments for homogenization. So, there are theory again about this. You can just check another resource about how to obtain these equations of the Scheil fundamental stuff. I want to go from the practical way here. So here you'll see microstructure of a Roth product, 4130 steel, has been hot rolled. So you'll see the banding, and this banding, the different bands come from the segregation during solidification. So in this table, we just place the general chemical composition, and we're going to try to calculate the different percentage of phases at 15% liquid and first 85% of solid composition. So 4130 is our base composition, and here I'm showing you, notice that I'm placing all of the elements included in the ASTM standard, plus some incidentals like copper, nitrogen, aluminum. Those are incidentals. So if we open ThermoCalc, we just click in Scheil solidification simulation as the first step. And basically, as you know, we have a flow here of information that we are going to follow. So the first thing is we are going to click in the different elements that we want to model. So I'm just going to go, obviously, first iron, and I'm going to go by our example here. So let me just minimize this screen here. This side, I'm going to place this one here so I can check. So I have carbon, I have nickel, I have silicon, I have chrome, manganese, moly, vanadium, copper, and I'm gonna go by nitrogen, sulfur, aluminum, and those are the all elements that I'm going to include. Okay, so basically it's placing the composition of all of these elements here in this table. So for example, carbon 0.29, nitrogen 0.15, and so on. So easy. But just the other thing that I wanna check here, so after we just place all of the chemistry, if we go to the phase and phase constitutions, we'll see that all of the phases that can be predicted by this model or by this database. So as you see here at the top of the system definer, also we have the database. In this case, we have selected the steels and iron alloys, which is the database that we usually use for steels. We also can take a package. So the package of steels and database, so basically that includes mobility database and the regular database. In this case, the mobility database are for diffusion analysis. We are not going to do diffusion analysis, so we can just delete it just to avoid, extra calculations in the system. So we just regular database here. But we can also use a different database. So we have the regular database. And in phase constitutionals, basically, here, obviously, the system is going to predict the more stable phases. And in iron carbon systems, we know that one of the stable phases is graphite. But we don't want to precipitate graphite because we know that this is not gonna be like, really stable. It's gonna be quasi-stable, basically. So we are gonna uncheck graphite, and also I'm gonna uncheck diamond, because that's also a really stable phase of carbon that, I'm not gonna obtain that. Obviously, in extreme conditions can obtain diamond, but not under regular industrial circumstances. The other phase that I'm gonna uncheck here is gas. Sometimes there are some gas produced, and there could be some gas produced during the during the solidification process, but sometimes this is just like kind of a kind of noises in the system. So I'm gonna uncheck gases as well. So those are the phases that I'm gonna uncheck. So I'm gonna enter my chemical composition and uncheck like the really stable phases. So let me just jump to my example here that I already calculated to don't lose too much time. So here I place all of my chemistries. And also I decrease my phases that I don't want. Now, I went to the Scheil calculator, and the starting temperature, I can start, really high temperature. I change to Celsius here, by the way. It's usually in default is Kelvin. I'm gonna change to Celsius. And I can start at 5,000 C, but it's gonna take a lot of time. So I know that usually still solidify, less than 1600 C. So my maximum starting temperature could be 1600 C, so I don't need to go too high temperature. Here is just the chemical composition. And notice that also there is an option in ThermoCalc, which basically select me the fast diffuser. Basically, a fast diffuser is a function that ThermoCalc use to, assume that some of the elements are going to diffuse faster in the solid, which basically is something that is not considered in the regular calculations. Also, I can place some of these interstitial like fast diffuser, but I'm just going to allow carbon to go fast diffuser. All right, now if I go to the plot render, notice that I also check Celsius here in temperature, and I'm gonna plot temperature versus mole fraction of solid. So the mole fraction of solid is gonna go from 0% solid to 100% solid. So in other terms, 100% liquid to 0% liquid. So after that, I just need to right click and perform now. So after doing that, basically it's going to perform these three. So it's going to perform all of these three. And after some time, it takes, some minutes to calculate depending on your system, it's going to give you this result. So this result basically is showing you all of the parameters that I was describing before. So basically go back here, the solidification range of the alloy. So basically the solidification range, you see basically is going from the melting point of the material that actually you can zoom, just click and drag, this window, and you can see here your melting point. Here you'll see kind of deviation coming from the probably the numerical result. But basically you can see that the melting point is around 1500 5 Celsius. So that's the melting point of the material in this case. If you drag in one of the axes, you just click and drag and basically go by the home again, default view. So starting to solidify at 15.5, and basically you'll see the phase. Well, first let's check here the two different curves that there are plotted. The first curve, the dot line, is the equilibrium. So if you just slow cooling, following the phase diagram of this alloy, considering all of the elements, the material are gonna follow this path, okay, according to your composition. But because the Scheil, because there are some diffusion effects or segregation effects, basically the Scheil calculation is following this color line. So this color line is the calculated by Scheil, the dot line is the equilibrium calculation. So that's answering the second part of the what is giving the Scheil calculation, which is the pressure of the solidus temperature to segregation. So basically we are saying that under equilibrium, the solidus temperature is 36 Celsius, as you see here. You know, I can also zoom. So basically here 1430 Celsius. And if I go by the Scheil, which is the color one, is 1403. So we have a depression of around 40 degrees, you know, and probably more, 40 degrees Celsius, just because the segregation due to the Scheil, okay? Scheil prediction. So that's the second part that is predicted by the Scheil. Now, I can also see the composition of the different liquids under in the dendritic regions. So I can just, what I can do is, you know, I just plot this curve using the regular standard parameters, as you see here in the example again, but you also can plot tables. So what you do is Scheil Calculator, right click, create successor, and table render. So in table render, basically it's a table that you are gonna create from the calculations that you did. Instead of plotting the experimental data in a plot or the simulation data in a plot, you are calculated in a table. So this table you can just rename, right? Just to check it. So in this case, for example, last 15% liquid, if you want to call it like that, but you can just put a reference. And for example, in this table, what I did was I put three conditions here. Mole fraction of liquid, the first, mole fraction of liquid, right? The second condition, I place composition of phase, and in this case, liquid. So I'm going to change to composition of phase, all, and all means all of the elements. I can select a particular element, for example, carbon if I want, but I want to see all of the components. And I can also place all of the phases, but that's going to take a while because there's a lot of phases predicting. I'm just going to select liquid, for example, in this case, and in mass percent. So that's the second part of the table. And the third part is just to also check temperature. So I just click plus, and I just put temperature here in Celsius. So that's the plot that I have here. Is the last 15% liquid. Basically, it's not the last 15% liquid, but that's the reference. So if I, you know, click in the plot or in the table, or if I click in this option here, in this sheet, you'll see that the first, obviously, is the mole fraction of liquid. So it goes to from 101. So this is fully percent liquid. And notice that in fully percent liquid, the chemistry of the chemical composition is basically the basic composition of our material that we enter, input, right? And in this case, the melting point is going to be 1505 for liquid temperature, okay? Now, if you go follow the table, you will see that the fraction of liquid start to decrease. Obviously, you have 0.99, so 99%, blah, blah, blah. So you go down. And here, for example, around, you want the last 15% liquid. So in this case, for example, you can take these two dots and interpolate, or you can take, you know, approximately this value as like 15% liquid. So 0.148 or I could approximate 0.15. Now, why 0.15 is important? So if I go here back to my slides, usually it has been determined experimentally and, you know, different researchers that the last 15% of liquid is basically the composition of the segregation area. So we can go by the 0.01%, the last 1% of liquid, but, you know, in that case, it's like kind of the last stage solidification. And remember that this is a really, you know, like a decent fast process. So when you are average, the last 15 of liquid is basically saying, okay, this last liquid that is solidifying is going to be my base composition for the segregation area. So that's why it's important, you know, the 15%, instead of going again. So, you know, 1%, which basically is a lot of segregation here, you know. In average, you know, you are not going to get that because, again, you know, you are high temperature. So you notice here, 15% is around 85% solid. So we have in this composition. If you have like almost 100% liquid, solid or 0% liquid, you have, some time where the materials can diffuse, high temperature, and, there is an average values here. So again, some researchers has found that, in some papers that 15% liquid is a good point to assume the composition. So if you go to the table again, you are going to notice here that you have a chemistry. So basically, that's the chemistry of the last percent of liquid. So for example, in this case, carbon is tricky because carbon is a fast diffuser. So in this case, it's telling me carbon is 0.8. So has increased from 0.29, which was the initial carbon, to 0.83. So the carbon has segregated. However, remember that carbon has a high mobility in steel at high temperature. So at these temperatures, I assume that the carbon can homogenize faster. So I'm not going to consider carbon. It's going to, not going to go that value. And that's something that's the point that I'm pointing here. As you see, carbon is getting constant. Now, for example, let's go by the next one, nickel, right? So nickel started at 0.15. That was our base composition. And when it starts to solidify, or the last liquid to solidify is 0.2. So has segregated, so 0.5 increase. So in this case, approximately 0.19. So by the way, this table was obtained by FactSage, a different software, which basically give us, similar predictions, but it's not exactly the same. That's what you have 0.1, 0.01 difference between my calculation in ThermoCalc in FactSage. I need to update this table, but, that's kind of the idea. Let's another segregated element. For example, molybdenum, which segregates really bad, right? So it started at 0.18. So if I check molybdenum in my table here, so it started at 0.18, 100% liquid, and the last 15% of liquid, my molybdenum goes to 0.38, 0.39, right? Which basically here is similar to my table, a little bit higher, calculated by FactSage. 0.41. So it's segregated really high. That's kind of the worst element to segregate. So that's the same analysis that I can do in the different elements. So that's for the last percent, the last liquid to solidify. So I assume that the more segregated areas where it's rich in composition are the last 15%. So those banding is related with that last liquid. Now, it's also important to know the first, in this case, first 85% of liquid, or I could say the first 15% of solid. So with the same assumption, I could say, the similar case for the solid. So in this case, the first material to solidify, assuming that is the center of the dendrites, which basically are the lean areas, I'm assuming that are the ferrite banding in this case. So here I calculated two tables. One table is for, as you see, basically, and I'm going to go to the plot again. So in the plot, you'll see that we have the Scheil calculation, and the first material that start to solidify, or the first solid that start to solidify is BCC A2. With BCC A2, as you know, is ferrite. So basically, this blue curve is going to be related with, in this case, high temperature delta ferrite. So first is forming delta ferrite up to 0.85% of solidification. We reach the peritectic point. So at this point, the material transforms to FCC. So this delta ferrite transforms to FCC plus liquid. So it's going to continue solidifying as FCC, which is austenite or gamma, right? Gamma or austenite. So at this point, it starts to solidify. And in the end of the solidification process, actually precipitate a sulfide. In this case, could be manganese sulfide, right? And you can check as well the composition, which you are going to see is rich in sulfur and probably manganese. So this is going to be a manganese sulfide. So at the end of the region, is going to obtain a precipitation of manganese sulfide, which sometimes when you, I don't know if here is clear, but here, for example, you can see there is sometimes in the banding, because this is the last liquid to solidify, you see elongated manganese sulfide, because basically that's predicted by the Scheil solidification. That's never predicted by, for example, equilibrium calculation, but it's predicted by the Scheil. So that's another part, interesting. But you can come and say, okay, what is the composition of the first 15% of solid to form, right? And in this case, you can think, okay, what solid I want? I want delta ferrite, or I want gamma ferrite, or sorry, gamma or austenite. In this case, it's more interesting to check the gamma, because that's the phase that is gonna go from this temperature to the other transformations. Delta ferrite is just for high temperatures, but we can check both. So basically, I'm just assuming here, calculating the first 85% of BCC, which is delta ferrite. And again, the same condition, so mole fraction of, in this case, ferrite, delta ferrite. So starting at 0, high temperatures, and go to 47%. And in this case, stop to solidify, and basically it's going to transform to austenite. So if I plus the austenite, basically the same, FCC, all of the components, and temperature. So it started almost 0 here, 1 to the power of minus 30 is almost 0. And it started to form at high temperature, but it's almost nothing. And as you see, basically started to decrease the temperature, and probably at this point I started to have a significant number of ferrite, or austenite, sorry. So I can assume what is the first 15% of ferrite. So, again, if I approximate, in this case, it's telling me the 15% of ferrite is around this value, 0.148. And this is at 1478 temperature. If I go to my plot, if I find 1478, it's going to be around here. So if I, put a horizontal line, I'm going to check that is approximately 15% of gamma that has formed at this point. So that's when this point is located. But the important part here is, what is the composition of this first austenite to form, because that's the lean areas in our microstructure. So again, carbon, carbon is not a big problem, because we have, diffusion, fast diffusion, so I'm not gonna consider that. But let's, for example, say nickel. So nickel here, our first nickel was 0.15, right? So the FCC is basically the same, 0.15. Silicon, 0.24, 0.21, so it's a little lean of silicon. Chrome, we started at 0.86, now it's 0.84, so it's a little lean of that. Let's check molybdenum, which is always the bad segregation factor here. So molybdenum, the base composition is 0.18, and remember that in the last 15% of liquid, it was much higher, 0.4. In this case, in the first 15% of solid, it's almost 0.14, 0.13 something. So it has 0.14. So it's lean in molybdenum. So these areas are lean in alloy elements, and the dark areas, which are the the last liquid to solidify, are rich in alloy elements. That's basically what it's telling us. So from these plots, we can extract this first, the Scheil diagram. So we can extract all of the information, including solidification, liquidus, solidus, depression of liquidus, and composition of different phases, and comparison between the Scheil predictions and equilibrium predictions. So those are all of the parameters that can be useful, predicted by the Scheil. And obviously that's gonna also help us to understand segregation, especially in castings, and as also is gonna help us to obtain heat treatments for this particular material. So that's kind of the summary what we obtained, right? So we have our Scheil calculations, have liquidus, solidus and liquidus temperatures and the different phases predicted. All right, so that's all for this Scheil modulus.